press the bell icon on the YouTube app and never miss another update.
Today we are going to discuss part 9 of current electricity. Here we are going to discuss about resistor. Right. A resistor is a device used to offer designated value of a resistance for the flow of electric current in a circuit, or a resistor is a device used to control current in an electrical or electronic circuits, right? Generally, there are two types of resistors: wire wound resistor and carbon composition resistor. So, resistor, right, it is a device used to offer designated resistance in a circuit. It may be electrical circuit or electronic circuit, or in other word, resistor is used to control current in a circuit. Now there are two types of resistors, right? They are, number one, wire wound resistors, right? So wire wound resistor are generally in the form of a coil. They are in the form of coils made up of the certain alloys like nichrome, manganite, and constant tan, right? Generally, they have a very high resistivity, at the same time, right, low temperature coefficient of resistance, and these resistors are bulky, that means quite large in size, and they are costly because we are using metallic alloys, and as resistance is directly proportional to length of the conductor, for the higher value of resistances we have to use longer resistance wire, right? Therefore its size will be more and it is also costly. And the second one, it is carbon composition resistor, right? So carbon composition resistor, right, is made of suitable composition of carbon taken in the form of a cylinder, or it is fused in the form of cylinder, right? Two, right, electrical wires are connected at the two ends. They serve as leads, right, for external electrical connection, and this cylindrical carbon is enclosed inside a ceramic case or plastic case, and that resistor is called as carbon composition resistor, right? It is consists of carbon composition, right, in the form of cylinder with two leads for electrical connections and enclosed inside plastic or ceramic case, right? Now these carbon composition resistors are, right, they are compact in size, very small in size, right? About cylindrical shape irutte, about 3 to 4 millimeter in length, and about 1 millimeter in diameter. It is such a very small size, and it has less cost. The cost is also very less. Even nowadays, for 1 rupees we can get right, several number of carbon composition resistor. So the important thing is carbon composition resistor are very small in size, that makes the instrument compact, handy, and they are less cost. Now, color coded resistor, right? Now we know that these resistors, right, are very small in size, therefore it is difficult to print the value of resistance on the resistor. Therefore the value of resistance of the resistor and the tolerance of the resistor, right, the percentage through which the resistance value can deviate from the marked value, that is called as percentage of error, or it is called as tolerance, right? And these are indicated by marking suitable colored rings or colored bands on the resistor, right? Such a resistor is called as a color coded resistor. It is like this. It is provided with two leads for electrical connection, and towards one side, right, we have marked the colored band, marked with colored band. Say this is colored band B1, second colored band B2, third colored band B3, and fourth colored band B4. Generally there will be 3 or 4, right, color bands are marked on color coded resistor, right? Now these color coded resistors, right, indicate resistance value and tolerance of the resistance value, right? Now here these colored bands, they represent the particular value of the resistances, right? Here generally the first band B1, it represents the first digit of resistance value. It represents the first digit of resistance value. Now the second colored band, it represents second digit of resistance value, that represents second resistance, and the third colored band, it represents number of zeros to be followed after the two digits, or it represents the multiplication factor, right? That is the two digits are multiplied by the appropriate power of 10, and this fourth digit, right, the fourth digit, that represents that tolerance. It represents tolerance of resistance value, right? See it, first digit, first band, first digit of resistance value, second colored band, right, second digit of resistance value, third colored band, number of zeros to be followed after the right two digits or multiplication factor, and the fourth colored band represents the tolerance, right? Then how to decode the color coded resistance, or how to obtain the value of resistance and tolerance by using colored, right, coded resistors, right? So here generally we are having 10 digits starting from 0 to 9. We are having 10 digits, right? Depending upon the position, right, of digits, right, it can have different values, right? Say this is now 1, this is 11, this is 100 and, right, 11, like that. Just here we are having 10 digits 0 to 9. So here these digits, right, are represented by different colors, right? Now here among the colors, right, black is the darkest color, and that represent the least value of digit, that is 0. The darkest color represents the lowest digit 0, and the brightest color, that is white, right, that represent the highest value of the digit, that is 9. The other colors, right, with increasing relative brightness, they represent the higher digits starting from 1, 2, 3, 4, etc. Right? Now, to remember this color code and to find the value of resistance and tolerance, we use a synonym. Right? Now, the synonym used to remember. Color code is, that is B Roy goes Bombay via Gateway. Here this first B, it represents black, and that is 0. The second B, that represents brown color, and it represents the digit 1. The third color is, right, red, right, that represents the digit 2. This O represents orange color, that represents digit 3. Yellow color is represented by white here, that yellow, that represents the digit 4. Now here G represents green, and that in turn represent the digit 5. Now this B represents blue, right? That blue represents the digits digit 6. Don't get confused. There are 3 B representing the colors. Here this is black, the darkest color, right? Now little more, right, bright, that is brown, that represents number 1. Here blue represents number 6. This is violet, it represents the digit 7, gray that represents the digit 8, and white that represents the digit 9. That means B. Roy goes Bombay via Gateway. The other synonyms are also there. B. Roy of Great Britain has a very good wife, right? I think this is easier for remembering one thing. So B. Roy goes Bombay via Gateway. The first letter represents the darkest color, that is black, with digit 0. The last word, letter W, that represents the brightest color, that is right representing 9. So remember, black 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, gray 8, and this is white, that is 9. So when we write it here, after remembering that, right. So B. Roy goes Bombay, black 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, gray 8, and this is 9. Now among the 3 or 4 colored band, the first 2 colored band, right, they represents the value of the first two digits of the resistance value. The third colored band represents number of zeros to be followed after the second digit, right? And the fourth band represents tolerance, right? So if we take, right, tolerance, so fourth band, it represents tolerance of resistance value, right? When we take this fourth band, right, so if there is no fourth band, that means there are only 2 bands, right? Now in this case, tolerance is plus or minus 20%. Right. Now if the fourth band is, right, silver, fourth band is silver, right, then tolerance is plus or minus 10%. If the fourth band is gold, right, then it represents tolerance is plus or minus 5%. Is that clear? Right. So first color represents first digit, second color represents second digit, third color represents number of zeros to be followed after second digit, and the fourth digit, right? If there is no fourth band, only there are 3 bands, then this resistance tolerance is plus or minus 20%, right? If fourth band is silver, then tolerance is plus or minus 10%. If the fourth band is gold, then the tolerance is plus or minus 5%, right? Using that, right, let us find number 1. To find resistance value of given color code. Right. So A, say we have given red, black, right, orange, gold. We have given the color code red, black, orange and gold. Now take this one. BB Roy goes Bombay. We know the rules, right? Here the first color represents first digit, second color represents second digit, third color represents multiplication factor, and the fourth one represents that is tolerance. Here this red, it is 1. Now this is red, it is 2, black is 1, orange is 3, right? So gold is plus or minus 5%. Now the resistance value becomes R is equal to, so this is 2, right? Now this is black is 0, not 1, brown is 1, right? Black is 0. Now 2, 0, the first 2 digit. Now see here, orange represents 3. That means 3 zeros have to be followed after the second digit. That is 0, 0, 0, right? O. Now the tolerance, it is plus or minus 5%. Or this can also be written as that is 20. That is the first 2 digit, right? Now this 3 represents the multiplication factor is 10 raised to the power of 3. That into 10 power 3 ohm plus or minus 5%. Or finally we can write R is equal to 2.0 into 10 power 4 ohm plus or minus 5%, right? So either you can write in the form of zeros or you can write in the form of appropriate power of 10. Now we will take up another example. Right, here green, brown, black, gold. Green, brown, black, gold. And now green represents 5, brown represents 1, black represents 0 and gold represents plus or minus 5%, right? Now if we write the resistance value, R is equal to first digit 5, second digit 1, third digit 0. That means number of zeros to be followed is 0, right? Or multiplication factor 10 raised to the power of 0 ohm plus or minus 5%, right? Or R is equal to this 10 raised to the power of 0 is 1. 1 into 51, it is 51 ohm plus or minus 5%, right? Is that clear? If the third band comes out to be black, that means there is no zeros to be followed after 2 digit, or multiplication factor is 10 raised to the power of 0, that is 1. Now see another one we take, that is orange, blue, red, right? Orange, blue, red. Here orange means 3, blue means 6, red means 2, that means 2 zeros, right? And here this is plus or minus 20%. Why? Because no fourth band, right? There are only 3 color codes here: orange, blue, red. So fourth band is absent. Fourth band is absent means, right, the tolerance is plus or minus 20%. Now let us write the resistance value. R is equal to 3, 6. 2 means it is not 2, 2 zeros, that you have to remember that one, right? Here the red is representing 2, right? That means the 2 zeros have to be followed after the second digit. 600 ohm plus or minus 20%. Now D, if we take right, yellow, right, violet, brown, silver. Now yellow represents 4, violet represents 7, brown represents digit 1, and this is plus or minus 10%. Now the resistance value comes out to be R is equal to 4, 7, third one, that is 1. That means 1 0, right, have to be added after 47. Now this is 1 0, right, ohm plus or minus 10%. This is how we can decode that one, right? You put certain numbers or refer any book, right? Then try to practice it, right? Just remember the synonym, right? And the colors, it is easier, right? The colors are with increasing order. Remember, this is the darkest color, black, right? Little bit high brightness, relatively high brightness, this is brown. So compared to brown and blue is more bright, right? Therefore it is 6, right? So otherwise there is no confusion here, only these B's, right? So B Roy goes Bombay via Gateway. First 2 colors represent first 2 digits of resistance value. Third color represents number of zeros to be followed or multiplication factor. Fourth band represents tolerance, right? That's all. Now, to write color code for resistance value, right? Now so far we have obtained resistance for given color code. Now we will write color code for the given resistance value. Say A, we have 2300 ohm plus or minus 5%. Resistance R is equal to 2300 ohm, that is 2300 ohm plus or minus 5%. Now the writing the color code, right? 2, that represents red, right? Now the second digit 3, that represents orange. Now the second digit is followed by 2 zeros. Two zeros means the number is 2. 2 is again represented by red. So red, orange, red. Then the tolerance is 5%. That is gold, right? So the color code for the given resistance 2300 ohm into 10 power plus or minus 5% is red, orange, red, gold. Now B, we have R is equal to, right, 5000 ohm plus or minus 10%. 5000 ohm plus or minus, right, 10%. Now this R is equal to, and resistance color code is equal to, this is 5 first digit, that is green. Now the second digit is 0. That means 0 represented by black. So second color is black. Now it is followed by 2 zeros. That means 2 means red. That means red. Now obviously it is silver. So green, black, red, silver, that represents the resistance value 5000 ohm plus or minus 10%, right? Right. Now we are having resistance, right? 5.3 into 10 raised to the power of 4 ohm plus or minus, right, 20%. All right. Now here we don't have, we have a decimal point here. This is not 53. In fact, this is 5.3. Remove that decimal point. That becomes 5.3 into 10 raised to the power of 5 ohm. Don't take it directly. The resistance value is always written in the form of the 2 digits after then multiplication factor. So there should be no decimal point. If there is a decimal point between first 2 digits, you remove it, right? Now this is 53 into 10 raised to the power of 5 ohm plus or minus 20%. Now R is equal to, right, 5. That is green, 3 orange. Now this is 5. Again green and no fourth color because the tolerance is plus or minus 20%, right? Now this is how we can write the color code for given resistance value or to obtain resistance value for given color code, right? You just you practice it just to remember that one synonym. BB Roy goes Bombay via gateway, and the colors, that is important, don't get confused. The first color represents the darkest color, that is the first letter. Here the white W represents the brightest color, and the colors are arranged with increasing relative brightness. Right. Now let us understand what exactly is the tolerance of resistance value. Suppose we are having resistance R is equal to 100 ohm. It is the marked value of resistance. Suppose if it is having plus or minus 5%, then the resistance can deviate, right, plus 5% or right minus 4%. So it can have the resistance may be it is equal to 105 ohm to resistance R is equal to 95 ohm, right. So only 5% variation, right. It can deviate from 105 to 95 ohm. Suppose we have R is equal to 100 ohm plus R minus 10%. What does it mean? Then here the resistance value may vary from 10% of this 110 ohm to, right, minus 10% of this. This is 90 ohm. This is how, right, the resistance value of the resistor can deviate from its marked value. Either it will go to 110 or 90 ohms, right. There is no much deviation. See here. Here the deviation is small. Here deviation is little bit more. Suppose we have R is equal to 100 ohm plus R minus 20%. Then here the resistance can deviate from R is equal to 10%, 20% of this one, 20. So 120 ohm to minus 20. R is equal to 80 ohm, right. Here percentage deviation is more, right. So here this resistance is more accurate than this resistance value, that is the tolerance of resistance, right. It gives the percentage up to which the resistance value can deviate from the marked value. Now another thing here, one thing has to be noted. So far what we have discussed here, all those resistors having resistance greater than 10 ohm. But if resistance value of a color code resistor is less than 10 ohm, then it has no fourth band. It has only 3 colored band, right, and the third colored band is either gold or silver, right. Here gold represents 0.1% of right the not 0.1%, it represents multiplication factor 0.1 and silver represents multiplication factor 0.01, right. Now that means if resistance of resistor is less than 10 ohm, that is R is less than 10 ohm, then, right, third band will be gold or silver, right, and there is no fourth band, right. Now here that gold represents, right, multiplication factor 0.1 or, right, 10 raised to the power of minus 1, and here silver represents, right, multiplication factor 0.01 or it is 10 power minus 2, right. Here there is no tolerance because the resistance value is less than 10 ohm, right. When the resistance value is smaller, then the accuracy is more, right. Now for example, right, if we take, right, green, yellow, gold. Green represents 5, yellow represents 4, gold represents 0.1. So R is equal to 5, 4 into 0.1, or R is equal to 5.4 ohm, right? So remember that if the value of resistance is less than 10 ohm, then there will be only 3 colored band, and the third colored band is gold or silver. They represents multiplication factor. Gold represents multiplication factor 0.1, and silver represents multiplication factor 0.01, right? Now that's all about color coded resistor. Now we will take combination of resistors. And by studying capacitor, where we have studied the combination of capacitors in series, capacitors in parallel, and capacitors in mixed grouping, that is series and parallel, right? Even in case of lens also, we have equivalent focal length of a combination of length, right? Now we can have, right, two thin lenses of focal length f1 and f2 placed coaxially in contact. Then the effective focal length is given by 1 by f is equal to 1 by f1 plus 1 by f2, right? And we are also having the two lenses separated by a certain distance, right? Now that becomes 1 by f is equal to 1 by f1 plus 1 by f2 minus d by f1 f2, right? Now here this is the combination. We see when I am using that spectacle, right? So actually I am using two lens, one the eye lens, another one is the spectacle lens. Now they are having a certain distance, right? Why it is doing so? Because, right, now the focal length of lens is available in standard values. To get the desired value of focal length, we can combine two or more lenses either in contact, right, or separated by a certain distance, right? In a similar way, right, a resistor is a device used to control current in a circuit. Now a current through resistor is given by I is equal to V by R. For given value of voltage, we need more current, then we have to use, right, less resistance. Or to get less current, we have to use high resistance, right? By changing the resistance, we can change the current. Now these resistors are available in standard values, just like currency notes. They are available in standard values in the market. But whenever we need, right, a desired value of resistance, a particular value of resistance in a circuit, right? Say for example 5.18 ohm exactly is needed, right? Now this cannot be manufactured. Somebody needs 5.1, somebody needs 5.2, somebody needs 5.05. That depends upon the functioning of the circuit, right? Therefore, in such cases, whenever the particular value of resistance required in a circuit is not available in market, then two or more resistors can be combined to obtain the desired value of resistance, right? And that is called combination of resistors or grouping of resistors, right? Now you might have seen the same thing in capacitors, series combination, parallel combination. Here again there are two basic combination of resistors. One is a series combination of resistor, another one is parallel combination of resistor, and of course sometimes we may use both series combination and parallel combination together, and that is called mixed grouping or mixed combination of resistor, right? Now in a similar way, how we have found effective capacitance of capacitors in series and effective capacitance of capacitors in parallel, we can find the effective resistance when resistors are connected in series, right? Now we will take, right now, resistors in series. A number of resistors are said to be connected in series if they are connected end to end, so that on applying potential difference, same current flows through each resistor, but potential difference is different across different resistors of series combination. It is just like this. This is resistance R1, this is resistance R2, this is resistance R3, right? We see it when we arrange the resistors end to end, it is equivalent to increase in the length of the conductor, right? See, this is the length of, right, R1. Now with combination of R2, there is an increase in length. With R3, again there is still increase in length, right? So series combination of resistors is equivalent to, right, increase the length of a conductor, right? Now, so a number of resistors are said to be connected in series if they are connected end to end, so that on applying a potential difference across the combination, same current flows through each resistor, but potential difference across each resistor will be different, right? Now let us consider three resistors, R1, R2 and R3 of different values connected in series, right? This is R1, R2, R3 connected in series. Now, a potential difference is applied across the combination by using a battery of potential difference V. So, we have applied a potential difference V, right, across the combination, right? This is, we take A, B, C and D. These are all the points, right? Now, when the circuit is closed, a current I is drawn from the cell or battery connected. You see the path of current. It flows from positive terminal to negative terminal. Therefore, the same amount of current I flows through, right, each resistor, because there is only one path between positive terminal and negative terminal. The rate of flow of charge, right, is the same, right, across R1, across R2 and across R3. Therefore, current through each resistance is same, right? But potential difference across a resistor, right, V is equal to IR, that is the product of current and resistors. That is, we have V is equal to IR. This potential difference across R1, it is I into R1. Potential difference across R2 is I into R3. Here it is, right, it is I into R2. This is I into R3, right. That means potential difference across, right. Each resistor is different. Let V1 be potential difference across R1. V2 be potential difference across R2 and V3 be potential difference across, right, R3. Obviously, this potential difference V is equal to the sum of the potential differences across the individual resistances, that V is equal to V1 plus V2 plus V3, right. Now, we have from Ohm's law, we have V is equal to IR. Therefore, potential difference across R1, that is V1 is equal to IR1, potential difference across R2, V2 is equal to IR2, and potential difference across R3, V3 is equal to I into R3. Now, what is potential difference across the combination? Now, potential difference across combination, V is equal to V1 plus V2 plus V3, or V is equal to, now this V1 IR1 plus V2 IR2 plus V3 IR, or V is equal to, taking I common, we have R1 plus R2 plus R3. Let us take it as equation number 1. Now, the combination of resistor is replaced by a single resistor. Now, we will replace the combination of resistors R1, R2 and R3 by a single resistor. Of equivalent resistance or P, right. So, the equivalent resistance of a combination of resistors is that single resistance that produces the same effect as the combination. For example, we are having two 10 rupee currency notes, right. Now, that two 10 rupee currency notes is equivalent to one single 20 rupees, right, note, currency note. So, the thing which we can buy using two 10 rupees notes can be by that single 20 rupees. Now, the single resistor is replaced by the combination. What is the condition, right? This equivalent single resistance, right, produces the same effect as the combination. Now, what is the effect of this combination of resistors, right? Why we are using resistor? A resistor is nothing but a conductor, right. One of the condition for obtaining current is, right, there should be a conducting path. Now, this combination of resistor R1, R2, R3 has an effect that it gives a current I when a potential difference V is applied, right. Now, let us connect the same battery or cell to this one. So, the potential difference applied across the single resistor is V. Now, the current flowing through, right, the resistance Rp is I. See here, when we apply a potential difference of V to the combination, we will obtain a current I. Here also, for same potential difference V, we are obtaining the same amount of current. Such a resistor is called equivalent resistor, and its resistance value is called equivalent resistance, right? Now, we have replaced, right, the combination of resistors by a single resistor, right, RS. So you will take R, yes, not RP, series combination RS, right, that produces the same effect as the combination, right? Now, right, for single resistor, right, now this V potential difference, right, is equal to I into RS. Let us take it as equation number 2, right, where I is the current flowing through the single resistor and RS is the resistance of that single resistor. Now comparing equation 1 and equation 2, we get, right, RS is equal to R1, or we'll take one thing, I into RS is equal to I into R1 plus R2 plus R3. So on both sides I get cancel. Now we have RS is equal to R1 plus R2 plus R3. Right. Now this is the expression for equivalent resistance of three resistors R1, R2 and R3 connected in series, right? Now see here, the effective resistance Rs, right, is equal to the sum of the individual resistances. So the effective or equivalent resistance of a number of resistors connected in series is equal to the sum of the individual resistances of the combination, right? What I have mentioned, this statement is called, right, law of combination of resistors in series.